Welcome back, everybody. Today we're going to be taking a look at rates of change. It's a topic in section 3.7. We'll get to the lecture notes here in just a second, but just wanted to remind everybody under the announcements and the video lectures and notes from March 23rd to March 27th. We have 2 class periods behind us. We did Monday and Wednesday. This video I'm recording right now will be for Friday. Things you have due this week. You have quiz 7, which is due by the end of day tomorrow, Friday. This video will probably go up on Thursday. You also have homework in WebAssign for these 3 sections. I realize it is 3 sections, but we're also a week behind, so because of the extra week of spring break. So this is the only week I think that'll have 3 sections on it. The rest of the week are pretty tame, but this is going to be a pretty heavy homework week for you. My apologies for that, but those will all be due on Sunday, March 29th at 11:59. Those are currently in WebAssign. So yeah, let's get to today's lecture. We are dealing with analyzing particle motion, among other things, but these all fall into a category of what we would call rates of change. So we're specifically looking at how to use the derivative to handle applied problems, and if you want to read more about this, and I encourage that you do so, this is section 3.7 of the textbook. Alright, so I want to start with a basic example here. Suppose you have two particles moving along the x-axis, and we're going to look at their trail for the time interval from 0 to 8. One particle, we know its position is given by this function. The other particle, we know its velocity is given by this function. So I want you to try it out, and you should be able to handle this without me saying anything more about this, because we've dealt with some position, velocity, acceleration problems already this semester. I want you to go ahead and try out this first example. On the interval from 0 to 8, when is this particle moving to the left? So I want to pause the video right here, work on that, and then come back and see if you got it correct. Alright, if you haven't paused, please do so. I'm going to take a look at this example with you. Let's start by calculating the velocity of the particle p. So if you have the position function given to you by the natural log of t squared minus 2t plus 10, the velocity of the particle p would be simply the derivative of position, which is the derivative of this natural log. Now we know from our experience with derivatives that when you take the derivative of a natural log, you take 1 divided by whatever's inside the natural log. But then chain rule, you've got to multiply by the derivative of what's inside. And so this will be 2t minus 2 over t squared minus 2t plus 10, which I would write as 2, let's say t minus 1 over t squared minus 2t plus 10. So this is my velocity, and now I have the velocity of both particles. I've got the velocity of q here, and I've got the velocity of p here. Now to answer this question, we're only really interested in p, but I'm going to go ahead and do something that'll pay off for the next couple of questions that I'm going to ask, and that is I want to plot a sign chart of the particle p's velocity versus particle q's velocity. So here's what I mean by that. I'm going to create a little timeline here. We know everything in this problem goes from 0 to 8. And I'm going to create 2 of these because I'm going to do one for particle p and I'm going to do one for particle q. Alright, so make a straight line here. Alright, so starting with particle p, which is the one that we just found. Looking at its velocity, I want to figure out the sign of its velocity, whether positive or negative. So it's clear that when t is equal to 1, the velocity is 0. Okay? Remember, if your velocity is 0, that means the particle is stationary. If your velocity is less than 0, that means the particle is moving to the left, which is what we want to find here. And if your velocity is greater than 0, it means the particle is moving to the right. So let's start with knowing where the particle is stationary. So for p, the particle is stationary when t is equal to 1. You can see that that makes the numerator 0. So if I come in and put down 1, then I know at 1 the velocity is 0. So I'm going to write the velocity values up above. All right, so all I need to do then is if the velocity is 0 here, this is a continuous function. Well, it does have some discontinuities at asymptotes in the bottom, but those don't exist on this interval. So at 1, the particle is stationary, so I need to check to the left and the right of 1. So if we check to the left of 1, all I'm really doing is testing a value between 0 and 1. So if I took, like, say, 1/2 and plugged it in, what would I get? So if you plugged 1/2 into this, so I'm testing. Now you don't have to write all this down, you can do it in your head, but I'm testing the velocity at 1/2. If I look and plug 1/2 into the top, I get a negative. If I plug 1/2 into the bottom, I get a positive. So negative divided by a positive would be a negative. So we know that we are moving to the left between 0 and 1. All right, are there any other points of interest? Well, no. I know it switches. It doesn't have to switch value, by the way. But if it's going to change, it'll change across. Remember, these are called critical points. Critical point is where the derivative is 0. If it's going to change values from negative to positive, it has to change across a critical point. So I need to test again between 1 and 8. So come over here to the side, just pick a value, let's say 2. If I plug 2 into the top, I know that's positive. If I plug 2 into the bottom, that's 4 minus 4, right? So that's 0 plus 10, it's also positive. So I know that I'm moving to the right past time 1. So for the first 1 second, particle P is moving to the left, then it momentarily stops at 1 second and switches and moves back to the right. I know because there are no other critical points between 1 and 8 that the particle cannot change directions once it starts moving to the right on this interval. If we do a similar thing, if we want to answer the question, by the way, the answer will be C, because the particle at time 0 is negative. If you plug 0 in, you will get a negative. So at 0, it's moving to the left already, which is why I included it. And then it stays moving to the left all the way up until 1, but at 1 it's 0, so you can't include 1 because at time 1 it has stopped. It has a velocity of 0. All right, if we do the same thing real quickly for particle Q. Particle Q, let me write down its formula, t squared minus 8t plus 15. I believe that this does factor. So looks like what? T minus 5, t minus 3. So it doesn't have a critical point at 1. Instead, its critical points are at 3 and 5. So we know it has a velocity of 0 there and 0 there. If I test it at 0 to begin with, plugging 0 into this graph, you'll see at 0 this has a value of 15. So I know initially this thing's moving to the right. All right, if I test between 0 and 3, say I test at 1, the value at 1 here is, I'm just looking at plugging 1 into these. I'm not actually plugging it into the function, I'm plugging it into each factor. So 1 there would make that negative, 1 there would make that negative, so you have a negative times a negative, which means that we are positive in that interval. All right, test between 3 and 5, so I'll test 4. If you test the value 4, 4 makes that factor negative, but that factor's positive. So you get a negative times a positive, which results in a negative overall. So now we're moving back to the left in this interval. And then from 5 to 8, let's say I'll test at 6. If I plug 6 in, I get a positive and a positive. Oops. So I know I have two positives times each other, so the velocity is positive in that interval, and we're moving back to the right. So this gives me an idea of exactly how the particles are moving based on their velocities. We're going to use this to answer a couple more follow-up questions. So on the interval from 0 to 8, when are the two particles moving in the same direction? Okay, so would probably do us a bit of good here to copy and paste this down. All right, so now that we have that, when are the two particles moving in the same direction? So both particles are moving either left, or both particles are moving right, and so on. So you can see here on the interval from 1 to 8, this one's always moving right. So 5 to 8, they both agree. And then it appears right here from 1 to 3, they agree. So you got to be careful here. I would say they never move left at the same time. And they move right when t is in the following intervals. Now, this little pitchfork symbol means t belongs to or t is in, and then I'm going to list the intervals. So first off is from 1 to 3, they're both moving right, but it doesn't include 1, and it doesn't include 3 because at 3 this one's stationary. So from 1 to 3, or, this is the mathematical symbol for or, it's called the union symbol, or from 5 to 8, but it doesn't include 5 because this one's stationary at 5. Even though this one's moving right at 5, this one's stationary. So they're both moving right from 5 to, we can plug in 8 real quick on both of those, and you'll see that both of these are moving to the right at 8 as well. So 5 to 8, but we would include 8 there. So this would be the correct answer here. And I'd love to see you use this interval notation. You could also say 1 less than t less than 3, or 5 less than t less than or equal to 8. That would be okay as well. All right, so find the acceleration of particle q at time 2. So acceleration of particle q. I'm going to go ahead and once again copy this down again because you're going to see how we're going to keep referring back to this. Okay, so acceleration of particle q. We know the velocity of particle q is, let's see here, the velocity of particle q is t squared minus 8t plus 15. Which means that the acceleration of particle q is the derivative of velocity. Remember, the derivative of velocity is acceleration. So this is just a simple power rule. We get 2t minus 8 or 2t minus 4. Now, I'm only interested in q, so I'm going to go ahead and erase the timeline for p. And I'm going to create a different timeline for q, but I'm going to list acceleration rather than listing velocity. All right, so we've got our interval from 0 to 8. I'm going to look at the acceleration signs. We know that acceleration would be equal to 0 when t is equal to 4. So I'm going to plot 4. I know my acceleration is 0 there. If I plug in, let's say, plug in 1, if you plug 1 into this value, so the acceleration at 1 would be negative, and the acceleration at 5, let's say, if you plug in 5, that would be positive. So I know I have a negative acceleration here and a positive acceleration here. Okay, so here's what you need to be aware of for this problem. And this can be very tricky. We're looking at it specifically. You were asked to find the acceleration of the particle at time 2. So time 2 would be right here. So at time 2, the acceleration at time 2, if we plug it into the formula, would be 2 times -2 or -4. Now, how do we interpret this number? Don't just assume that because this is negative, that the speed is decreasing. You can really get yourself into trouble. Where it comes down to is what you need to know in terms of speeding up and slowing down is things are speeding up when, give myself some more room here. Particles are speeding up, or the speed is increasing, when the velocity agrees in sign with the acceleration. In other words, if both velocity and acceleration are positive, then that means you're speeding up. If both velocity and acceleration are negative, that also means you're speeding up. You're just speeding up in the negative direction. Slowing down or speeding down is when velocity and acceleration disagree in sign. So if one of them's positive and the other one's negative, then the particle will slow down. So if you look at specifically this problem for time 2, at time 2 the acceleration is negative, but the velocity is positive. So since they disagree in sign, the object is moving to the right, but it's decelerating as it's moving to the right. Therefore, we would say that at t = 2, the particle q is slowing down. So it's very important that you remember when it comes to speed, speed is different than velocity. Speed is the absolute value of velocity. Because of that, you have to have agreement in the sign of both the velocity and the acceleration. So it's very important that you remember this when comparing the two. All right, finally, find the total distance traveled for the particle. So I'm going to go back to the distance function or the position function we were given at the very beginning. It is this. And we also calculated the velocity. The velocity, if you recall, turned out to be right here. Was the function 2t minus 1 over t squared minus 2t plus 10. This thing was equal to 0 when t was 1. That was our critical point. So what I'm going to do is create another timeline. Make this one a little bit larger here. So t = 0 all the way up to t = 8. Now, here's the thing. I know at t = 1, this thing's going to stop moving, but I want to look at, because it changes directions. If you go here for the velocity of particle p, we change directions. We're moving to the left initially, but then we move to the right after stopping at time 1. So what I want to do is look at what is my position at these different points. In other words, I'm starting at time 0, but I'm actually moving to the left. Oh, whoops. That's not what I wanted to do. I did not want to do a time graph. My apologies. If you need to erase that, please do so. I actually want to look at the position along this graph. So this is the measure of position. And I want to start with position at time 0. So if you look at xp at time 0, this is natural log of, 10? Plug in t = 0? Yeah, natural log of 10. So I know initially the position at time 0 is given to me by natural log 10. Now, I know based on the velocity graph that I did above, I'm going to start moving to the left immediately. So at time 0, we're moving to the left because our velocity is negative. So this thing's going to move to the left, and after it gets to time 1, it's going to start to move back to the right, and it's going to finish somewhere over here at time 8 to the right. So the particle moves to the left initially, then it moves back to the right. And it only has this one critical point where it changes direction. All right, so I need to figure out what is the position over here at time 1. So the position at time 1 would be the natural log of, this is 1 minus 2, which would be -1, so it's natural log of 9. So after 1 second, we're over here at natural log of 9. All right, let's go forward to time 8. And if you plug 8 in, you'll get 64 minus 16. 64 minus 16, so 48. Plus 10, so this is the natural log of 58. So I know that's my ending position over here. So the question asked to find the total distance traveled by the particle on 0 to 8. So the total distance would be what? Well, you went from natural log of 10 to natural log of 9. So the distance here would be equal to the difference between the natural log of 10 and the natural log of 9 plus the distance from natural log of 9 to natural log of 58. So natural log of 9 minus natural log of 58. Now, you may be tempted, and we could calculate this to get a decimal. I'm not really interested in that in here, but you could throw this into Desmos real quick and get exactly what this is. The mistake a lot of students make on this problem is they assume that you just take the natural log of 58 and subtract the natural log of 10, because natural log of 58 is where you ended up, natural log of 10 is where you started, but that ignores this distance that you traveled, because if you just subtract this point and this point, you get this length. And that ignores the positive and negative directions that you traveled here, which were actual distance. So distance involves absolute values. You can't get around it. Displacement, right? The displacement after 8 seconds is different. Displacement is simply the difference between your starting point and your ending point. And this one, you should not use any absolute values because you want to know, so displacement is end minus start. So here that is the natural log of 58 minus natural log of 10. That is going to be a positive value, which means that the object moved to the right, displaced itself to the right over 8 seconds. It's further right of where it started. You always want to do end minus start so that you can get the correct sign here. If we had moved to the left further over time, then this would have been a negative quantity. The total distance, however, will always be positive. You can't have negative distance, but you can have negative displacement. So I just want to make sure you understand the difference between those two quantities. All right, these are the kinds of questions that you may be asked to work on when it comes to analyzing particle motion. And this is the main application out of section 3.7 that I want to make sure that you're able to do. All right, let me look at a couple other related problems. These are problems in different areas of science and different areas of science and applied mathematics. This isn't particle motion, but this is electrical charge. So if you have a quantity of charge, which charge is often measured in coulombs, that's passing through a wire, then the rate of change of charge is current. In other words, the derivative of charge is current. Now we typically use Q for charge and I for current. Now here is the charge function for the charge flowing through an electric fence. What I want to know is what is the current that's passing through the fence 2 seconds later. So if I want to know the current 2 seconds later, Well, that's the derivative of the charge after 2 seconds. And the derivative of the charge would be the derivative of this function. Evaluated at t equal to 2. So let's take the derivative first. Remember, you always take derivatives before you evaluate. So if I take the derivative first, we've got 3t squared minus 2t plus 1. And we're going to evaluate that at t equal to 2. So plugging in t equal to 2, I get 3 times 4 minus 4 plus 1. 12 minus 4 is 8, plus 1 is 9. So make sure that you're using the correct units here. The units for current are amperage. So 9 amps of current. Okay, moving on to the follow-up question. When is this current at its lowest amperage? So our current function, we calculated right here. This was the current, because we took the derivative. So if this is our current function, this function I of t is minimized, or minimal, when so we haven't talked a ton about this, but basically the way you want to handle something being minimal is when it has a critical point. Now, we're going to say a lot more about this in the coming weeks. Understand that when an object has a critical point, that critical point could be either a maximum or a minimum, or technically could be neither, because it could also be an inflection point. We've talked a little bit about that in class. But for this specific function, I'm relying a little bit on your knowledge of the fact that this is a parabola and you know what parabolas look like. So, you know, whatever this graph looks like, I know it passes through 1, so it's probably looking something like this. And I know it opens up because it has a positive leading coefficient. So this point here would be the minimum amperage. And the idea is this point is a point where the graph changes from having negative slopes to having positive slopes, which means at this point it has a slope of 0. So places where a graph has slopes of 0, those are potentially critical points. So I'm setting this equal to, I'm setting the derivative of this equal to 0. Remember, the critical point is where the derivative of a function is equal to 0. So the derivative of this function would be 6t minus 2. That's equal to 0 when t is 1/3. So after 1/3 of a, I believe the units here are seconds. Yes. So after 1/3 of a second, we've achieved a minimum amperage. So the amperage at 1/3, if I plug it back into my current function, at 1/3, we have 1/3 minus 2/3 plus 1. So this is negative 1/3 plus 1, or 2/3. So 2/3 of an amp. So I don't have a very well drawn graph. Didn't know what it looked like just off the top of my head here. Let me redraw the axes for you. So let's see, that would still be positive. So something like this. At t equal to 0, it has a value of 1. And over here at t equal to 1/3, it has a value of 2/3. So the minimum amperage is 2/3 amps. So that's the minimum amperage that this particular fence would ever have. And 2 seconds after the things turned on, we're back over here around 9 amps. Okay, so this is typical of a lot of these kinds of problems. It's typical in the sense that these problems often result in just giving you a function like this, taking the derivative of the function, answering some questions about where that derivative is evaluated, and then taking the derivative of that to tell me about maximums and minimums. So you can expect questions like this to occur, but there's really nothing special to teach on these because every situation is different, but the mathematics remains the same. If you want to learn about rate of change, the rate of change of charge is current. Rate of change implies derivative, so if you want to know about current, you take the rate of change or the derivative of charge and then evaluate it. There are many quantities in science that have function-derivative relationships, and this is just one example of those. All right, let's take a look at another problem. So another type of application problem that you need to be aware of are problems that involve cost, revenue, and profit. And there are two different important quantities when it comes to cost, revenue, or profit. There's average cost or average revenue or average profit. Average cost is the total cost, which would be price, divided by X is the number of items, so total number of items, which means that this thing has units of price per item. And it should make sense that this would give you the average cost, because if you're producing, say, 1,000 units, and you know what the cost associated with that is, if you calculate the cost associated with producing 1,000 units, and you divide by 1,000, that'll tell you the cost per unit. So the total cost per unit or price per unit. I probably should say cost here instead of price. Price would be if we're looking at something like revenue, so cost per item. However, I don't want you to get confused, because if we use the phrase marginal cost refers to the derivative of a quantity. So if you talk about the margin of a quantity, that's typically referring to the rate of change of that quantity. It's a financial term. But the marginal cost is the derivative of cost. Marginal revenue would be the derivative of revenue, and so on. So the marginal cost also has units. So also has units of cost per item. However, the two have very different interpretations. The interpretation of average cost is the cost to produce a single item on average. However, marginal cost, and we've talked about this earlier in the course, when it comes to the derivative, the number that you would get out of this function would tell you the expected cost for producing one more item. So if you were going from 1,000 to 1,001 items, then C prime of 1,000 would tell you the expected cost increase for producing one additional, the 1,001st item. So they both have the same units, but they have very different interpretations, and I want to make sure that we can sort through that. So here's just a little example to get you started with here. I have a cost function. I want to know which of the following best describes the marginal cost when X is 100 and when X is 900. So I'll let you pause, read through these answer choices, and then we'll talk about it together. All right, if you haven't paused yet, you should do so and try to tackle this problem. But what we have basically here is an understanding of what's going on in terms of producing items. The idea is, as you produce more items, the cost to produce each additional item goes down. That's why factories are useful. So the correct answer here turns out to be C. The cost to produce an additional item at a production rate of 100 items is greater than the cost to produce at 900 items, because the cost per item produced is higher at 100 than it is at 900. At 900, you're dividing by more things, so your average cost is less per item. So your marginal cost is also less because it's less per each additional item that you're producing. So the two things, marginal cost and average cost, are often related, but they don't have to be. So let's take a look at a couple of examples. What is the average cost when x is 100 and when x is 900? So our cost function here is negative 0.02x squared plus 50x plus 100. And we're looking at this on the interval from 0 to 1,000. Now, my recommendation for you is to use Desmos to actually do the calculations here, or use your calculator. Don't try to do this by hand. I'm going to write it down, and then we're going to switch over to Desmos here in just a second. So average cost, usually for average, we use a bar above the variable. So average cost would be bar C. So average cost would be the cost divided by the number of items. So the average cost at 100 items would be the cost at 100 items divided by 100. We'll get that here in a second. And then the average cost at 900 items would be the cost of producing 900 items divided by 900. All right, so let's take a look at Desmos. Just to keep everything here in the screen. So hopefully you're able to see that okay. All right, so let's start. I'm gonna plot my cost function real quick. So I'll call it C of x. And if I wanted to see it, I know that my interval goes from 0 to 1,000. So I'm gonna set the x-axis from 0, let's do like negative 10 to 1,000. And I know that it has a intercept of 100 here. So I'm going to go all the way up to 100 for my y-axis. Something's going on here. Should be able to see it. Maybe it's because I called it C of x. Oh, plus 100, not plus 1,000. Still, it's giving me a rather weird... Oh, there it comes back down over there. Where's the maximum here? Oh, really steep curve. Okay, so it looks like it maxes out around 32,000. All right, so sorry, just trying to get my bearings here on the x-axis. So let's do, like, say, negative 10 to 1,000, and then we'll do, say, 0 to, what is it, 32, 35, 34,000, something like that. So there's what my cost curve would look like. So here's a good representation of this cost curve. Okay, so now that we've got the cost curve in here, I do want to call it C of x, by the way. And you can clearly see here, it tells me my maximum cost would be, if I produce 1,250 items, my maximum cost is 31,350. Remember, we're only really dealing with this function on the interval from 0 to 1,000. So remember, you can change the domain. And that's what I'm going to do. So this is our function. And I'm interested in the average cost and the, here in a second, the marginal cost. So let's just ask Desmos to do this for us. So C at 100 divided by 100, this is the average cost. $49 per item. So if you produce 100 items, it costs you $49 per item, approximately, to do that. If instead you produce 900 items, then the cost per item gets smaller. That's what the previous question was about. The cost per item here would be about $32.11 per item. Okay, so this is how you would compute average cost. You could also compute marginal cost really easily. So marginal cost would be C prime at 100. So remember, you don't have to write down the derivative function. Desmos can take care of it for you. So C prime at 100, the prime symbol is the apostrophe symbol on the keyboard. So C prime at 100 would be $46 per item. Now remember, to interpret this differently, when you say $46 per item, what you mean is it's an expected increase of $46 in cost for producing the 101st item. Remember, that's what that means. And if I look at it at 900, what we would expect to see is to have a smaller number because my average cost is less at 900, so I would expect the average increase. So I'd expect the increase at 900 units produced to be less than the increase at 100, and the slopes bear that out. If you look here at the slope at 100, it's steeper than the slope at 900, so it flattens off. But I can look at the marginal cost at 900, and that's only $14 per item. So the expected increase of $14 in cost for producing the 901st item. All right. So one more question to ask here, and that is marginal cost the same as marginal average cost? In other words, is the cost increasing at the same rate the average cost is increasing or decreasing? Are those two quantities the same? Well, to answer that, we know marginal cost. So if C of x is our cost, we know that C prime of x is our marginal cost, because remember, marginal means take the derivative in this context. We know that the average cost is given by this. And so the marginal average cost would be the derivative of this quantity, which, because that is a, let me make this bigger again. So because this is a quotient, I should use quotient rule. So U is C of x, so U prime is C prime. V is x, so V prime is 1. So this will be U prime V minus U V prime, which is 1, all over V squared. So this is C prime of x over x minus C of x over x squared. So what I want you to see here is that this is not the same as marginal cost. It's not the same at all. In fact, this is the average marginal cost minus this sort of correction factor. So the idea here is that the marginal cost and the average marginal cost are not the same thing. They don't increase at the exact same rate. They don't have the exact same behaviors, but they are kind of related. All right. So our final example for this lecture, we're going to take a look at a this is called a logistic curve. If you've never heard of a logistic curve before, they can be used to model many things, including ongoing spread of diseases that we're dealing with in the world. A lot of the curves that you've been seeing lately on the news, a lot of these are logistic or exponential related curves. If you want to learn more about the spread of diseases, we talk about that a lot in the differential equations class, so you can look forward to that at some future date. But here I'm just looking at the spread of a rumor. So suppose that I have a population and P of t is the proportion or percentage of the population that's heard the rumor so many hours after it began. A and K are just some positive numbers that control the spread, and I want to analyze this function, make sure we understand it by answering a couple of questions below. So I'm going to start with, let's say the limit as t goes to infinity of p of t. I want to look at long term what happens according to this function, according to this model. Well, we know the way that limits work at this point in the course. So the limit of the fraction is the fraction of the limits. I would take the limit of the top and bottom. I would then bring the limit inside up until it hit a function of t, which is the e to the minus kt term here in the denominator. So the limit operates just on this function of t right here. And what is the limit at infinity of e to the minus kt? Well, if k is positive, then this would be a decay exponential, which means that its limit over time is 0. So the limit of this is 1 over 1 plus a times 0, which is just 1. Now, how do we interpret that? Remember, p of t is the proportion of the population that's heard the rumor. So if the proportion of the population is 1, then this 1 represents 100% of the population has heard the rumor. Which makes sense. If you let any sort of rumor go long enough, eventually it will infect the entire population. Okay, so that's the answer to 1. What about 2? So question 2 says find the rate of spread of the rumor. So the rate, that's what this whole lecture today is about calculating rates of change. The rate of spread of the rumor is the change in time of the rumor, or the derivative. So if I take the derivative of this function, it's taking the derivative of this, and I know a lot of you want to do quotient rule here. Let me advise against that. Let's instead treat this like the following. This is 1 plus ae to the minus kt raised to the negative 1 power, and that's because this is in the denominator. So now it's just a power function with a little bit of chain rule. It's an easier problem to differentiate now. So if I take the derivative of this, the power comes down. It's negative 1 times all of this. Subtract 1 from the power, then we're going to multiply by the derivative of the inside. So this is the derivative of the inside. The derivative of 1 is 0. The derivative of a, ignore the a, take the derivative of the exponential, which would be a negative k e to the minus kt. So you've got negative 1 over this quantity squared times a to the negative k e to the minus kt. Or when you simplify, there's a negative here and a negative here. So negative times a negative will make a positive, and you'll end up with ak e to the negative kt on top, and 1 plus a e to the minus kt squared on bottom. So this is the rate of change of the rumor spreading. So this tells me how quickly the rumor will spread based on the values a and k that we might be given, and you can calculate it at a particular time. So this is the derivative of p prime of t. It's the change in the proportion as a function of time for this particular rumor. All right, let's go back to Desmos real quick, because I want to take a look at this one in Desmos as well. So we'll get rid of these that we've already worked here, and let's just enter a new function. So remember, the function here we're working with is this logistic curve. So I'm going to enter that in as p of t equal 1 over 1 plus a times e. Remember, you can't just enter e, you have to do exp. So e to the minus k times t. And I'm going to add in values for a and k. And I know because this is a proportion, I know that my population, which is the y-axis, will range from 0 to 1. And since x is time, the x-axis is time, then 0 to, let's say, 24 hours might be appropriate. So you can see that we're almost there. We've got a good graph here. So after about 10 hours, it looks like, we're really close. Yeah, after 10 hours, if both A and K are 1, everyone in the population would have heard it. So if you look at how K controls the graph, K controls the rate at which the population spreads. Remember, this is only for values of t greater than 0, and I'll just say t greater than 0. So this is our model, and you can see that as K changes, the bigger K is, the quicker everybody hears the rumor, the quicker we reach saturation. If K is smaller, the less time it takes, and if K is negative, then people will forget the rumor. It doesn't make a lot of sense here. Remember, K and A were positive for this model. So the values of K between 0 and 1 are the important values. They're sort of the percentage growth, if you will. So this would be like the rate of change is like 20%. 20% per hour kind of get exposed to the rumor. A equal to 1 changes where the starting amount is, kind of. It's sort of related to the reciprocal of the starting amount, but it changes where we are along the y-axis. So this is called the logistic curve. What I want to do real quickly is I want to also graph p prime of t, which it may not let me do. No, it's not going to let me do that. Okay. So instead, here's what I want to do. We came up with it together. So here's our formula for the derivative. So I'm just going to go ahead and type that in. So we've got a times k times e to the minus kt divided by 1 plus a times e to the minus kt, all of that squared. For some reason, it's not letting me do it in terms of t. Let me call this function f of t. Okay. So we know f of t is the rate of change of this thing. And what I want you to notice is wherever the rate of change has a maximum, that corresponds to the steepest increase in the rumor being spread. So here, there's our maximum of the rate, and that's the steepest it's being spread. You can see that as we increase k, that maximum happens sooner, and so the virus, or the rumor, if you will, spreads even quicker. So you've probably seen some curves like this on the television lately, and I just wanted you to understand kind of what you're seeing there is a little bit of differential equations, a little bit of calculus involved in the determining of models for the spread of these diseases. So the last question that was asked here, we've kind of already answered it though, is graph this for the case a equal 10 and k equal 0.5. So let's do a equal to 10 and k equal to 0.5. Okay. How long will it take for 80% of the population to hear the rumor? So 80% of the population would be 0.8. If I just graph the curve 0.8, so that would be y equal to 0.8, then that happens right here after about 7.378 hours. So about 7.4 hours into it, 80% of the population would have heard this rumor. Estimate when the rumor is growing fastest. So when is the rumor growing fastest? Well, the maximum of the rate, the maximum of the derivative function here, occurs after 4.6 hours, and it's growing at a rate of, remember this is a percentage, it's growing at a rate of 12% of the population per hour. So that happens at about 4.6 hours. That's the fastest rate of growth on this curve. All right, it's very important that you're able to take some of these application problems like this and drop the functions into Desmos, and then be able to answer questions like this that involve comparing a function and that function's derivative to determine things like we did in this problem. All right, that should get you a really good start, and I will post this Desmos graph for you online, so you can take a look at what we did here. It's very important that when you look at the homework for section 3.7, you understand that there's going to be circumstances on that homework that we haven't discussed. There'll be quantities we haven't talked about. Maybe it'll be a problem from biology, or maybe it'll be a problem from chemistry. But the point is, the techniques that we discussed in this particular lecture carry over to those other situations as well. Finding rates of change involves finding derivatives and then interpreting the quantities that you get from those derivatives correctly. All right, y'all have a good day. Talk to you later. Bye.